Hi, I'm Matt Eland, and let's talk about some common data, AI, and application architectures. If you're not familiar with me, I do a lot of really weird and nerdy stuff. My background is primarily in software engineering. I have a master's in data analytics focusing on machine learning. I'm also Microsoft MVP in .NET and Azure AI services, and I have written a few books and courses as well. My books are around C Sharp and .NET development. Um, if you are looking to do machine learning in .NET, I have a really good book on that. If you're looking to undo some bad code in your past history, well, I have a book on that as well. And I'm working on my next book, which is around C Sharp projects and really being able to do fun and nerdy stuff with .NET. In addition to this, I have a couple of courses out there on LinkedIn Learning, which focus on AI topics, so go check those out. Now, I should also share my biases. Now, everybody who's going to be teaching something has biases from their own backgrounds, and I'm no different. My background is primarily in .NET, in software engineering, and in working in smaller organizations. I also have a very heavy bias towards Azure. I've worked with AWS before as well, but you're going to see a lot of my examples and iconography, etc., are based off of Azure types of things. In this talk today, we are going to be talking about software architectures, AI architectures, and data architectures as well. And we're going to really break this into three main chunks. And my goal is to give you a good understanding of the common architectures that are out there and the ways that they might break or the ways that we might test them or improve them. Okay, so let's jump into this with a discussion of software architectures. There's a lot of different ways of building software, and this has changed significantly over the years. Software architecture has changed from when I was a new developer to where I am today. And I think that's great because the needs of software engineers have changed over the decades as well. But before we talk about these specific architectures, let's talk about what we're actually deploying because that's changed as well. So deployment models, when I started out as a brand new junior software engineer, mid-level software engineer, when we were talking about deploying something, it was usually to a individual server. And this was often, in the case of these small organizations I worked for near the beginning of my career, this was also often a machine that someone had in a back closet somewhere that was running IIS or some other type of server software, and you would run your application on that, and it would respond to requests from the internet. This was a very bad idea to run from an organization's closet, but you would eventually graduate to more of a professional setting where you'd rent some space in a data center downtown or something like that, and you'd have a spot on a rack or maybe a full rack where you could go in and put in your software and your equipment. Now, this was still a pain because you had to maintain that hardware. You had to maintain the operating system on that. You had to maintain the updates to it. You were somewhat responsible for the security and the cooling and the just ongoing maintenance of these devices. And if your needs changed, well, you now needed to go and upgrade your server, or you need to go buy a new server and build that and install that and transition off your old one. Okay. Now, companies like Azure and AWS and Google came along and they said, hey, you shouldn't have to deal with the hardware components if you don't want to. We're going to give you platform as a service. And this means that we're going to operate our own data centers and you tell us what you want to deploy on them. As long as you're using one of these things that we support, we offer environments that have these types of technical stacks and these versions in these technical stacks. Well, we have that stuff that we're maintaining and you can just go out and deploy it already onto our stuff. And the nice perk about this is that I'm no longer responsible for physical security and cooling and maintenance and and power backups and all these things for my equipment. But also, if my needs change and all of a sudden I need a beefier server, well, I can upgrade more easily because I'm just upgrading the type of service that I'm renting from the cloud provider. Now, this is very similar in some aspects to another common approach that people have had over the years and still have to some degree, and that is using a virtual machine or VM. A VM is basically it's a server that you have running a hypervisor. And this hypervisor is basically simulating a bunch of child operating systems inside of the server. And so you'd have one really beefy machine that's sharing its memory and sharing its disk space and sharing its graphics cards, etc., with these child operating systems. But the perk of this is that it can run multiple different operating systems independently using this hypervisor, and so it can simulate three or four or five different computers inside of its own physical computer. And as the needs of your applications change, you can give it more and more and more of your system resources. As you launch a new application, well, you don't necessarily need to get a new server anymore. Just need to figure out which virtual machine is going to be deployed to. So that was really neat. But over time, we did discover some inefficiencies with this, and we said, "Hey, we're really repeating a lot of the disk and memory and all these other footprints of our operating system." And so we said, "Hey, let's switch to a containerized architecture, so using a platform like Docker or Podman or something else." And now we're saying, like, "Hey, instead of using a hypervisor, we're going to use a container engine. This container engine is able to run containers that have these common dependencies on them." And so we're no longer needing to support the operating system, all these different containers. We're paying for it once on the container host. And that is then able to use more of its horsepower to power the individual containers, and the containers are smaller as a result. And so this has really helped redefine what it looks like to build software, because we can build containers and we can deploy those containers to these different hosts, and watch them run in those environments with different environment variables and connections and things like that. So containerization has been a really nice development for us as software engineers. There's another architecture out there that we need to think about, and that's serverless architectures. Now, serverless architectures do have servers. There's many of servers, actually, but those servers are running a very specific environment that the cloud hosting provider has set up. And when we are working with a serverless architecture, we're writing our application just as a small individual function using exactly the specifications and supported languages that our cloud hosting provider says. So if it's Azure, we're writing an Azure function that adheres to the common contracts of an Azure function. And we deploy that function. And whenever that function needs to run, it gets loaded onto the next available machine that's all running the same stuff. And it says, okay, here's our code. We're going to run your code now. And basically, our application can go in and out very quickly because it's loaded onto this system that's already running, and it's able to take anything that looks like a common function it can deal with and process it. So this is really good for when you have cases where you have very small pieces of code that need to run infrequently, or cases where you don't really necessarily need to have something running all the time, because it can help you with costs and agility as well. So this is really, we're talking about what we are deploying. Now, let's talk more about the configurations of these things that we are deploying. When I first started out, we were really working with client-only architectures. This would be an application would be delivered to somebody. Maybe you'd download it from the internet. Back in the olden days, you'd get it on a 5.25 or 3.5 inch floppy drive, and you'd put that into your computer and you'd install it. Maybe install a series of disks, but you'd have something running locally. It might be an app that you download from the App Store onto your phone. Whatever it is, it's a self-contained application that runs locally on your device. If you lose internet, that's fine. Your application still runs because it has everything it needs locally. Now, this is great, except for the ways it isn't, which makes sense. That's just software engineering. It can't talk to external resources necessarily. Well, sometimes they do, but typically you don't share information with other users. And so when you have a situation where you need to have information available outside of just your device, well, that starts to fall flat a little bit. And so we saw the emergence of kind of a multi-client environment where you'd have multiple clients usually deployed on the same network, or virtual network, and they would be running your same software, and they would be talking to shared resources such as a shared database or application server or something else like that. Okay. Now, this is really handy because now we can have different people in your organization communicating with the same data. So imagine the Bureau of Motor Vehicles or some other place where you have a bunch of people needing to query the same basic information about your account. Well, they're sharing the same data, and so now they can. Now, the ways this falls apart is that if you need to change your database schema, if you need to update your client applications, you really should be updating all of it at once, because if you're having one of your applications running version 1 and the others are running version 2, now you can start to get some inconsistencies going on. Additionally, if you have one of your applications get stolen, like let's say someone breaks in, steals a laptop or something like that, well, now someone has access to that client information, and that may even have the credentials to access the database, depending on how you're configuring your security. And so that can be a nightmare as well. So to help deal with this, we've switched to more of a client server architecture where you have a bunch of different client applications and they're communicating with this server. And the server kind of acts as a little bit of a buffer between these clients and your databases. This is really good from a security perspective because you no longer need to store secure connection information in the clients or even have the clients able to touch the database at all. And it's also better from an update perspective because your server can have a V1 API and a V2 API, and you can have them both running in parallel. And your clients can get updated to work eventually with a V2 API while some are still on the V1 API. So it gives you some added levels of flexibility while also having some extra complexity in there because you now have a new service that you are maintaining and running at all times. And so people looked at this and said, this is great, but sometimes it gets overloaded or we have a lot of teams and this is just a lot. And so let's, instead of having one server, let's have two. So we started having these in-tiered architectures where you have one server running for the domain layer, one server running for the business layer, one server running for, whatever it might be. You'd have all these different layers and these would be different servers, often maintained by different teams, and they'd kind of communicate with each other. Now, this is additional complexity. This is additional time needed to communicate from one server to the other. And whenever you have anything like that, you now have more things that can break. But it does help teams work sort of independently of each other by using kind of these shared contracts and how they communicate with each other. So that was good-ish, but it did have some downsides. Nowadays, we often have more of a serverless architecture approach, where we have these individual functions that might run in reaction to some sort of event. And as a result of one function running, they might trigger another function. And so instead of having these in-tier architectures, we would have these event-driven architectures where we'd have events flowing from one system to another. We're going to talk a lot more about this as we go. But first, let's talk more about the growing pains that most organizations encounter as they go and how these impact our applications as we're delivering them. So, as organizations grow, they're going to find that the solutions that they offered to 10 concurrent users don't work for 100 concurrent users or 1,000 concurrent users or many different clients with different security and privacy and scalability needs. And so they start to bump into different ways that they need to scale their applications. Usually the first thing a startup often will need to do is they'll need to scale vertically. So they're going to take their server that's now starting to get overloaded with the requests that are coming in, and they're going to make it a larger server. They're going to upgrade the RAM, they're going to upgrade the processor power, whatever it might be. They're going to move to a higher SKU that can handle the level of traffic that they're getting from the different clients. Right? So usually you are paying an extra price for your compute resources in this case, but it's not that much more. And this tends to be the kind of upgrade that most startups hit first. So that's really, really good. Now, this does hit a point in time where you start to say, hey, this is too much. From moving from SKU 1 to SKU 2 wasn't too bad, but moving from SKU 2 to SKU 3, that's a much more significant price tag. And so for that, you start to say, hey, instead of scaling vertically, let's scale horizontally. Okay, so with horizontal scalability, you're now adding a load balancer to the mix. And so now your requests are going into a load balancer, and that load balancer is routing them to one of the different servers that are waiting in your pool of servers. All these servers are running the same identical application and they're ready to take requests. And so when a request comes in, it goes to one, maybe at random, maybe the next one in a sequence to take a request, maybe the one that has the fastest throughput at the moment, whatever it might be. But it's getting routed to one of these servers and that's able to handle it. Now, the nice thing about this is that you can dynamically add servers to your pool when you're having higher demand traffic areas. So if your users typically use your application first thing in the morning and then right at the end of the week, well, you might know in advance that's going to happen, or you might respond to metrics as that happens by adding more servers to your pool. And then as things quiet down, you might remove those servers from the pool and save your costs that way. So that's really good. The other thing this is good for is if a server starts to fail due to maybe hardware or whatever it might be, well, it just gets removed from the pool and maybe you add another one back into the pool dynamically running the same software. And so it gives you a little bit more fault tolerance as well for when random things happen because things do happen over time. Now, the problem with this is that you now need to build your applications differently. Instead of being able to store information on one individual server, you are now running in more of a stateless mode where any request it can go to any server. And the same client who's communicating with your servers, the first request might go to server one, and the second request might go to server three. And your application needs to be built in such a way that that's okay, that you are not that you're not requiring any sort of a session information that's stored locally to your individual server. So it's a different paradigm for building applications, but it can help you with really more dynamic scalability concerns. Now, after we've addressed the web server issues, typically the next thing that happens is you start encountering database issues with database performance slowness. This is usually going to be keyed around a few really critical tables that you have inefficient queries around, or a lot of reads, a lot of writes to. You're going to have your traffic jams in really a few common key core spots, is what I've observed from most organizations and most client organizations that Leading Edge works with. So, one of the things you can do about this, as kind of an early stopgap, is you can add a caching layer. So with caching layer, we are no longer reading directly from the database in many cases. We're now checking an in-memory cache to say, hey, do we have the information that I need in this cache? Is it valid? Is it fresh? And if it is, I'm not going to query the database for it. So if my query was really slow and inefficient, and I have that cached already, then great, I'm just going to grab that value. Otherwise, I might run the query and cache the result. So the next time I run it, it's going to be there for me to get out of memory. And so this really reduces the strain that you're putting on your database as a result, because you have this cache. This is often through a service like Redis. There's a number of different ways you can do caching as well, which is really cool. Now, caching is complexity, and it is an additional cost, because, of course, it is. uh, with this complexity that we have with caching, we now have certain bugs that can come in, because if we have a cached query about, let's say, a specific user, and then another request comes in and updates that user, well, if someone were to read the cached version of that user, they get inaccurate information that didn't have the updates from the write. And so whenever we do a relevant write, we need to invalidate things in our cache that would have been impacted by that write. So this is a new thing that can break in our software, because A, the cache can be unavailable, and B, well, you can forget to clear the cache or invalidate the cache for things that are impacted by a write operation. So really good way of improving your database efficiency, but another way that things can break. Another way that we can improve our read efficiency for databases is by using a read replica. With a read replica, data is asynchronously copied from the primary database to the read replica. Now, that's not instantaneous, so your read replica may have slightly stale information, but if you don't need your information to be completely accurate as to this minute, then this is usually fine, and this can help you out quite a bit. And most services, such as Azure, will have an option for giving you an automatic read replica without you having to do much of anything for this. Read replicas are really good for things you might do a lot of analytical processing around that you don't want to overload your primary application database for either. So that's really nice. Now, if complexity is the answer to a lot of our problems, then a lot of complexity has to be great, right? So, some really smart people introduced this concept of command query request segregation, or CQRS. And CQRS basically seeks to address the problem of writes to databases can be slow. Reading from complex queries can be slow as well. Let's solve this with two databases. With our write database, we are now basically logging new events. We're just doing raw inserts into our database, saying, hey, this new event happened. We're going to record it. It's going right into this table, and we're going to process it later on. With the read database, this is our materialized view, we are storing our data in a way that is denormalized for querying. So instead of having to do a lot of complex queries, we're now able to go in and we're able to select from a very specific materialized view that's built specifically for our data needs. And this is really cool because it's going to be very performant, because we're just reading data from something that's built to be read from. Now, the way that this works is that we have an asynchronous process that goes in and it takes those events and it uses those events to construct the materialized views. Now, that happens asynchronously. So your data in your materialized view is not going to be immediately consistent, but it will eventually be consistent. So this is why you'll have data that gets updated every so often, or it takes a little while for your changes to be available to other people. It's often because you have an asynchronous situation like this, where data is eventually consistent with other people. It doesn't necessarily mean they're using CQRS. There's many things that have these kinds of symptoms. CQRS is really good for optimizing your write performance and optimizing your read performance, but you pay for that in terms of complexity, both in terms of running two databases and in terms of the logic needed to synchronize between one and the other. Additionally, you pay for this in the price of eventual consistency because it's now very hard to get immediate data states. But if you don't need that, this can be a really efficient architecture if your complexity needs justify it. Of course, you can also add a cache to this as well. Typically, you don't necessarily need a cache for reading because your reads are going to be very performant from this database schema, but there's no reason you can't have anything like that. So these are some of our common application architectures, but we haven't talked about microservices yet. And so we're going to spend this section talking specifically about what microservices are, the headaches they can cause, and the problems that they're designed to solve. So when we think about microservices, or when I think about microservices, I'm thinking about a solution to two specific types of problems. The first problem, and this is the one I typically think of, is going to be the team problem, where we have a team that's now getting very large. When you have a large team working on a large piece of software, there's often going to be overlaps between the different areas. And so you'll have a lot of unintended consequences when you're modifying one area that unexpectedly modify other areas. Additionally, it can be difficult to coordinate with other developers to avoid scenarios where you are blocking other developers or accidentally breaking things that they are working on at the moment. It gets harder and harder to make larger changes the larger your team goes when you have a monolith application scenario. So, to solve this and also to give us additional flexibility in terms of scalability, people said, hey, let's look at more of a microservice based architecture. And a microservice architecture involves many different services that are smaller in nature. They have their own pieces of data, and they are able to communicate with each other. And so, what this lets us do is it says, hey, we're going to have team one maintaining this microservice, and team two is going to go out and they're going to maintain these other few microservices, and team three is going to modify these microservices. And so, you now have more distributed ownership of your application, and your developers can specialize in different areas. Now, the trade offs in this is that you now have fewer people who understand the overall flow of the whole system. So that can be harder as well. Additionally, you now have more things that can break. We'll talk more about that. But you do get some perks from this as well. First of all, you can scale each microservice independently of each other. So if you find one is overloaded, you can scale that in a different way than you might scale the others, which is really nice way of doing things. Additionally, it gives your teams more independence because now you can say, hey, this team gets to work with whatever technology they want when they're implementing their microservices, and they can use their own data store in whatever database technology or database provider or database format that they want to use, right? And so it gives teams more autonomy and freedom, which is always great for teams and morale and just flexibility for an organization. And in fact, you may find that you don't even necessarily need to have individual services. You might be able to do this with something like functions. So using more of a serverless architecture, you might have a series of functions replacing these types of things that you might see ordinarily with your microservices. Now, if you don't want to use serverless applications or Azure Functions or something like that, you can always use containers for this. So you can have one container representing an individual microservice. And this can be really handy for when you need to dynamically grow the number of services you have or dynamically scale the number of services you have. So that is an option for you as well. Uh, this becomes more challenging when you need to be able to say, hey, how does this service relate to this service and how do these things connect to each other? That's when you start to get into more orchestration scenarios where you start to need things like Kubernetes and to sort of say, hey, how do we dynamically scale? How do we handle failures? How do we connect these things to these other things, right? That's where we get really, really, really enterprise scale. But often organizations don't truly need that level of scale, and they jump to them early at a huge financial cost and a huge complexity cost when they could have been focusing on more modular architectures that maybe would have been a better fit at the time based on the load level they were seeing and anticipating. So microservices have gotten a bad rap recently because of their brittleness. With a microservice-based architecture, you now have a whole lot more complexity in your system, and you also have to worry about failures. So, hey, how does my microservice handle it when your microservice is down? How do I handle it when the database is down? My service is running, but its database is suddenly offline. When you have a system with a lot of different components, you have to plan that some portion of the time, some of your services will go down randomly due to hardware or networking or other types of issues. This may be brief, but it will eventually happen at enough complexity levels, at enough time as your application grows, as your user base grows. These things happen. It's just natural entropy in software engineering. And so you need to start to think about how are we handling failures. And one way of handling failures is just with more resilient code. So using application logic, for example, I'm a .NET developer. I would use a library in .NET like Poly that gives me retry logic. So with a library like Poly, you can say, hey, my call from this microservice to this microservice, it failed. I'm going to retry again in half a second. Okay, well, that failed, so I'm going to retry again in a second. Okay, that failed, so I'm going to retry again in 2 or 3 seconds or whatever it might be. You got a certain degree of randomness in there as well, so you're not overloading your systems. So you have sort of these resiliency policies and exponential back off that help you deal with things becoming offline. Um, but that only gets you so far because sometimes things just really are offline for quite a while, and your application needs to be able to handle that. One of my favorite ways, or probably my favorite current way of handling this, is through the use of topics. And with topics, we are no longer directly tethering one microservice to another. Most of the time, we're saying, hey, an event just happened. I'm going to publish this event to a topic. Okay, so let's say here we have something like um, a user has purchased an item from my online store. Okay, I'm going to publish the purchased topic. And other services can choose to subscribe to that particular topic. And it can say, hey, my service needs to care about this. When this event happens, tell my service about it. And so each service that cares about this purchased event can subscribe to that topic, and then it will get notifications when that topic changes. The nice thing about this is that if my application goes offline, if one of my microservices goes offline, well, its its notifications don't go away. They're still available for it to query. This is because we're typically using queue-based notification systems with our topics. So anything that's subscribing to a topic has its own queue. And when this event happens, this event gets inserted into the queues of anything subscribed. So you might have one event, but it's getting inserted into the queue of anything that's subscribed to that event. And so that way, if I have an application that certainly has an issue, such as something's not able to pull from its queue, well, that's okay. The message is still in the queue. When that service comes back online, it's going to say, okay, what did I miss? And it's going to be right there in the queue for it, and it's going to be able to pull and handle that. The nice thing that queues give you as well, in addition to this fault tolerance, is queues give you a way of kind of independently scaling, right? So with this queue-based approach, we are now able to independently scale our application because I can now run two different versions of a service, and they're both running from the same queue, and they're just going to say, hey, what's the next thing in line? And one of them's going to handle the next one, and one's going to handle the one after that. And you're now burning through your queue twice as fast. So if you have scenarios where your queue is just getting too long, well, you can just dynamically scale up and have another service running. And then when your queue gets more manageable, you can scale it down, which is really nice. One theme I'm hoping that you've picked up on so far is that complexity is everywhere. These systems have different levels of complexity, and they exist to serve different needs that different organizations are going to encounter. It's very hard to remove complexity from a system, but it's usually very easy to add complexity to a system. So you want to fight complexity as long as you have by choosing only the things that you absolutely need. So, are microservices really the solution? Well, sometimes. If you have a very complex domain, if you have a lot of developers, you have a lot of very independent teams that need to build a lot of different things together, then maybe microservices might be a good fit. If you really have like a Netflix level dynamic scalability type of need for your individual services, then yeah, you might want to consider microservices. One of the reasons we get microservices to begin with is people look at the complexity in their monolith and say, this is unmanageable. This is legacy code. I can't deal with this. I need to take more and more out of this thing. You might take some of the things that you might need to scale the most dynamically or things that are causing you the most pain. You can say, hey, I need to get this out of my monolith. I want to put this into its own microservice. And that's when you start to say, hey, I'm going to go in, I'm going to take a vertical slice out of this. I'm going to say, hey, find me everything related to a specific feature. And now we're going to take that section of the application, we're going to chop it off, and we're going to make it its own independent microservice with its own team running it. And everything else is going to still be in our large application. Okay. So in those types of scenarios, then yeah, you might have a really good case for a microservice when you are trying to retire an older application bit by bit by bit, right? There's a common pattern out there called the strangler fig or banyan tree pattern, where you basically have this tree that's getting slowly replaced by all these roots that kind of creep up, and they start to really be form this parasitic relationship with this tree, and they sort of eat the tree from the inside, and the original tree eventually dies, and it gets replaced by this network of vines. Now, this metaphor says, hey, we're going to do the same thing with our old legacy applications. We're going to slowly chop off bits and pieces from this legacy application, and we're going to make them into their own new application, their new modular microservice or whatever it might be. And we're going to go on there. So we're going to go in there and we're going to chop off bits and pieces of this application, and we're going to put it either into a new monolith or we're going to put it into its own microservice. But either way, we're going to take it out of the legacy one that we're trying to retire. And so over time, you have a smaller and smaller and smaller legacy code base, and you have your applications getting kind of continually renewed as you chop things off and you put them into a new place. Now, this doesn't have to be disruptive to the people already calling your code. There's patterns like API gateways and things like yet another reverse proxy that help you with this. Basically, your applications are still talking to the same API, but now things get routed differently. So instead of things getting routed to your legacy application, things are now getting routed to the new version or new microservice or whatever it might be. And this API gateway, that gets you a little bit of resiliency from the issues that you might have. And so as you retire things, as you move things from one service to another, this gives you that flexibility going on. One of the most exciting things in modern software architectures at the moment is this idea of a modular monolith. A modular monolith is going in and saying, like, hey, we're going to take our monolithic application, but we're going to intentionally make it as modular and decoupled as we possibly can. So our concerns are truly separated. We might have different assemblies or projects for different pieces of our system, and we've engineered in such a way that they physically cannot talk to the other ones. And so now you have teams that are focusing on some of these modules that plug into your larger monolith. And you have other teams that are focusing on your cross cutting concerns, such as logging, database access. They're talking about compliance, security, all these things. And they're enabling all these other teams who are focusing more on their individual modules to succeed. And so you now have this monolithic application you can still work well with, but you have teams that are insulated from each other and from these inadvertent changes that a disorganized architecture can have. There's also ways that we can go out there and reduce risk in our applications and how we are deploying things. One common way that we see is with a feature flag. So we might deploy a new feature or deploy a change, but it's not active yet in that people are still using the old implementation of something. And you can add a feature flag that says, hey, after a certain date or with certain types of users, or just randomly with a certain percentage of users, we're going to enable this new feature, right? And so this lets you sort of beta test your new application features to a small subset of users without impacting everybody. Okay. Now, feature flags can be messy because organizations who adopt them often will not remove them in a timely manner after the fact, even when the feature is completely on and you're never going to turn it off at this point. And so they can add this additional complexity that you need to go back and clean up at some point in time. But they can help you deploy your code gradually and gracefully and deal with errors and early feedback as well. There's also this idea of blue green deployments where you have two different environments running, and most of your users are on the blue environment, let's say, and you're doing a release, and you're going to update your green environment with nobody using it. And then you're going to start to drain some of your users from the blue environment to the green environment. And you're going to monitor that. And you're going to make sure that nothing is going wrong in that green environment. And as long as things are continuing fine, you're going to eventually move all requests into the green environment. The blue environment no longer gets any requests, and then it goes offline until the next deployment when you're going to swap from green to blue. And so you sort of have these two differing environments that can be available at the same time during a deployment. So that's going to help you deal with these scenarios where you are now just trying to work through the uses of your application and trying to deploy software without any issues. So an additional degree of resilience there, and this is kind of baked into your cloud hosting providers as well. So that's a nice feature you have for you. Another library that I've particularly liked for very niche kind of applications is something called Scientist. This is by GitHub. It's a library that basically says, hey, we're going to deploy an experiment. We're going to have an old way of doing something and a new way of doing something. And we're going to have everything go in, and they're going to call the old way, and it's going to get the result from the old way. Let's say that we are calculating the price of something, right? So your requests are going to go in, they're going to get the price from the old way of doing things, and they're going to continue on as normal. But the system, secret to the user, is also sending that request to the new pricing system, the new one that you are evaluating, that you're looking for problems with. And it's calculating the price. And what Scientist does, is it says, hey, we're going to take the legacy version and the new version, and we're going to compare the results. Did their prices match? What were the performances like? Do we have any exceptions in this new one? And if you have significant deviations, well, they get logged into a database or table or whatever you're going to do, and you can review them as a development team and say, oh, hey, our new system, it works pretty well, but we did find this flaw that we didn't know about. Now, with Scientists, you got to be careful that you're not doing certain actions twice. So, for example, if your old implementation and your new implementation both send an email, well, that email will be sent twice. And so you need to design your system in such a way that you're not taking these destructive actions with your experiments. But it can be a really good way of just saying, hey, is our new system doing exactly what we think it's doing at a larger scale? Is it able to handle the level of load, the level of complexity that we might find from real world usage without introducing the same level of risk, which is really cool. I like that. So with deployments, your goal is really just small, frequent, automated deployments that are supported by tests. If something hurts, you want to try to do it more. Organizations that have really big releases have really big backlogs of bugs when they do this. And they often will slip their releases to next week or next month or whatever as they're trying to get everything ready for the release. And then inevitably, something gets out that's bad because it's too large or whatever it might be. And now you are in a panic and you're trying to manage it. Organizations that are in this mode, if they can commit to a more frequent deployment basis, it usually addresses these problems over time by getting them better at doing these releases and having the releases be less challenging because they're more regular, they're more automated, they're more predictable, right? Something's not ready, okay, it goes into the next release. Okay, we're gonna get stuff out early, we're gonna turn it off with feature flags, whatever it might be. Right? So these are some ways that we have of managing this complexity with software engineering and trying to insulate the user from these types of bugs that might occur. All right, so this is it for common software architectures. If I missed something that's interesting to you, please let me know. I'm always trying to learn about new architectures and new trends. If you find something was maybe incomplete or could be more accurate, let me know as well. This is something I want to write more about in the future and make more videos about. So if you have advice for me or more things for me to check out, I'd love to hear it because I'm always trying to learn and there's just so much out there. But happy coding and stay tuned for part two.